Hi there. I'd like to discuss a little bit about polar coordinates, just kind of set up the framework of them, why they're important, and how we do some basic conversions from Cartesian to polar, and also how we set up an integral in polar coordinates. So polar coordinates can be really useful if we have a shape that's kind of like this, for example, and maybe we're looking at the area in between, in this region here. If you get some kind of circular shape like this, you'll find that polar coordinates are, it's a lot easier to set up integrals with it. So that's kind of our motivation here. First, we'll go ahead and look at Cartesian coordinates. So typical Cartesian coordinate system you're pretty familiar with. You've got your y-axis, you've got your x-axis, and if we got some point here, we'll call that point xy. For our polar coordinate system, we're going to set up a little bit differently. So say this is our origin here, and we got this point over here. We're going to go ahead and call this distance here r. And if we've got a axis down here, then this angle here we'll call theta. And just to kind of put these coordinate systems together, of course this distance here is going to be our y value, and the distance down here to that point. And if you remember the phrase so, ka, toa, that's how I remember it, right? So the so means that our sine of theta is going to be equal to our opposite over our hypotenuse, and cosine of theta is equal to adjacent over our hypotenuse. And we know this opposite here is that value that's opposite of this angle in our triangle here. So that opposite value, the way we set it up here, is going to be y. And the adjacent value, the way we set it up here, is going to be x. So this is going to be equal to y over r, and this is equal to x over r. Where, of course, r is going to be our hypotenuse value here. So what we can do here is we can solve for x and y, and that kind of sets up our conversion. So based on this, we say that we can find x and y, where our x is going to equal our cosine of theta times r, and similarly our y is going to equal r times our sine of theta. And one last important connection we need to make here is this is a right triangle, of course, then we know we have an equation for our hypotenuse based on Pythagorean theorem, and that is going to be that r is equal to the square root of our x squared plus our y squared. So let's go ahead and box this in, because this is going to be some important conversions that we're going to work with. We're also going to have to look at this in terms of integration, so let's take a look at that. And for that, maybe we can scroll down here a little bit. And let's go ahead and bring in a couple plots here too that are going to help out. All right, we'll bring in sort of our Cartesian plot here, and we'll bring in a polar coordinate system over here. So what we're really looking for here is a way to express our typical integral or double integral over some region D of our function, typically of f of xy dA. And we're going to want to find a way to express a similar integral in polar coordinates. So this dA is pretty simple in rectangular coordinates. If you imagine we have sort of a grid over here, and this is my dA. It's pretty easy, because all that is we got our dx component here, and we've got our dy component here. So dA is simply going to be the shaded region, and here is just dx dy. This is a little bit more tricky in polar coordinates. So let's say that we're going to call this section right here our dA. Now it looks kind of like this rectangle over here. We can kind of treat it like that with these two dimensions here. And this dimension here, this way, is actually pretty easy. We can actually just call that dr. And you notice that's going to be same for all these grids. If I did a dA down here, dr is going to be the same. because we're just going to increment r at a standard rate here. This distance down here, oh, that gets a little trickier. And let's call that dc for now. So what we're trying to find here is we're trying to find this dA area here. Do that in red. And we know that's going to be equal to dr times r dc. But the reason I call this c here is because you can kind of think of this in terms of the circumference. So if we go ahead and drew a circle at this particular radius here, it might look something like this. And thankfully this app helps my circles look a lot nicer. And so if that's our circumference, we can make an equation for it and say that our c is equal to 2 pi r. Now, if we just wanted to find this dc value, well, that's not actually too bad. So our dc value is just going to be that our circumference that we found, that whole thing, and we're going to multiply it by the fraction of theta that we have here as compared to this whole 2 pi theta range. And so we can denote this fraction of a theta here that we're just looking at. We'll call that d theta. And so our dc is going to be our d theta divided by that whole theta range, which is 2 pi. So we can go ahead and plug in our expression up there for c, and so we have our dc is equal to 2 pi r times d theta, all divided by 2 pi. And of course you can see that this 2 pi cancels out, so we're just left with our dc is equal to r d theta. So we can go ahead and plug that in up here for our dc. So our dA is going to be equal to our dr multiplied by our dc, which is r d theta. So this is our dA, and that's sort of the tricky part about converting this into a polar integral. So what we can do with that is go ahead and write in here our general expression for a double integral in polar coordinates. We got this region D here, and instead of f of xy, we've got f of r and theta. And our dA, we're going to go ahead and plug in what we had down here. So it's going to be r dr d theta. And zooming out a little bit, just to summarize, we looked at how to convert between rectangular and polar coordinates, and how to find x, y's, and r's, how they connect to each other, and then we looked at how to set up an integral and change it from a Cartesian coordinate integral down to a polar coordinate integral. What we didn't talk about was how to find this region D here, but we'll talk about that in the next video. So stay tuned, and until then, take care.